Okay, hi everyone. So we are going to continue working through um, the next two sections of chapter 2. After we get through sections 2.1 through 2.3, you have enough information to finish homework number 1. And then later in the week, we'll start into section 2.4, which continues on into chapter 3 to see how that goes. And that will help us with homework number 2. So this video really is going to work to establish the vocabulary that we need to be able to understand everything that we're talking about over these next over this entire unit. Okay, so we will talk a lot about the bulk. And this is really some nomenclature, some language that we use as physical chemists. So before we think about what the bulk is, we want to think about our definitions of system, surrounding, and universe. So the system, that is the thing that we are studying. So it can be our solution inside of our flask. It could be a specific molecule that we are interested in inside of a balloon. It could be a single molecule inside of this solution. So maybe that was a horrible benzene, but maybe there's a benzene molecule inside of this, and we are interested in that benzene molecule. So our system is basically what we are interested in. Then, after we define what we are interested in, the area surrounding the system is known as the surroundings. So technically the surroundings go forever. Forever is a tough thing to measure in chemistry. And so really we define surroundings as the area outside of our system that we are interested in. Then we have to have some sort of barrier. This can be the glass of the container. This could be the walls of a balloon. This can be the edges of an atom. Ultimately, we need some sort of boundary that is separating the system from the surroundings. And then the universe is defined as everything: the system, the surroundings, and the boundary. Now, some notes about the boundary. The boundary defines how the system and the surroundings can interact. Okay, what do I mean? I mean that if I'm thinking that my system is held inside of a flask that has a lid on it, like the one in our picture, the boundary is solid. That means that the volume of our system cannot change. But if I were to pour the system into a balloon and tie the balloon, then suddenly our boundary allows the volume of our system to change. We make a key assumption that the boundary does not contribute to the thermodynamic parameters such as volume or energy, and therefore does not appear in the calculations. Okay, this kind of makes sense to us when we want to know the volume of our system. We measure the gradations on a graduated cylinder. We don't worry about how much glass is in that graduated cylinder containing our volume. Okay. So in our discussion thus far, in section 2.1, we really were thinking about an individual molecule. And we were asking things like, what is the total energy of this molecule? And we said that the total energy is going to be our translational energy plus our rotational energy plus our vibrational energy plus our electronic energy. When we were thinking about a single molecule and thinking about the properties of this molecule, in our case, energy, we were thinking about microscopic properties. So this is the behavior of molecules when we're considering a single molecule or a very small group. These are generally governed by the rules of quantum mechanics. So if I have one benzene molecule or even 3 benzene molecules, I have to study these as microscopic things. But whenever I have my flask containing a whole bunch of benzene, then suddenly my properties of my single molecule are not really the same, or they're not the same properties that we want to measure. And so the properties of the sample are known as macroscopic properties. And this is the behavior of molecules when there are large collections of molecules. And what we try to define is what is hard to define is what is large. And really, large is a sample that we can see. Once we have a drop, we have enough individual molecules that drop of benzene or water is governed by macroscopic properties. It turns out that there's some really interesting science and research happening at that borderline between when we have a sample of, say, 10 benzene molecules, and that small aggregation doesn't quite fit microscopic properties and doesn't quite fit macroscopic properties. And so there is a barrier and a transition between how big of a sample is big enough. But for our purposes this semester, we're going to assume that any system that we are studying is large enough to be displaying macroscopic properties. Okay, so amongst the macroscopic properties, there are really 2 types. There are extensive properties and intensive properties. Extensive properties are things about the system that can be determined by adding up the contributions of individual molecules. Okay, what do we mean? If we have, say, moles, amount, the number of molecules that we have is an additive property. So our moles is a count. The more molecules we have, the more moles of molecules that we have. Another thing would be volume. So as I add molecules to my system, my volume increases. And so if I know the volume of an individual benzene molecule, then I can add my volumes of my individual benzene molecules together, ... I can add each of those volumes, and I will eventually, if I'm clever enough, be able to calculate the total volume of the system. Then there are intensive properties. And these are things about the system that can be determined by averaging the contributions from the individual molecules. So if we think about temperature, that my individual benzene molecule, remember we said temperature is a measure of kinetic energy. It has some amount of kinetic energy moving around. But the overall temperature of my flask of benzene molecules is not the sum of the kinetic energy, the total kinetic energy. Instead, it is the average kinetic energy. And that means that temperature is an intensive property. Turns out that there are lots of things that are intensive properties. That is the average of what we see from a single molecule. Okay, so some examples. Extensive property, the number of molecules. Extensive property, volume, the space occupied. Energy, remember that we said that E total is equal to E translational plus E rotational plus E vibrational plus E electronic. And so energy, we are adding these together, is an extensive property. Intensive properties that physical chemists care about, pressure, so the force per unit area exerted by a molecule on the surroundings, that the total pressure is the average force. Density, the average number of molecules per unit volume, that's number density. Or mass density, the mass per volume. And there are many, many more of these. Okay, so your now try this problem is to identify the following as intensive or extensive properties. You have temperature, entropy, mass. And if you can think of other properties, you feel free to add to this list. I'm happy to check your work. Okay. Keep coming to office hours, keep asking good questions, and keep posting to the discussion board. You guys are doing